So, we want to discuss this solution of differential equations for this the coming maybe a week or a couple of weeks from now. And differential equations are all very common to all of us in various branches of science and engineering. And we come across almost in every sphere, every rather topic of science and engineering, we come across differential equations that need to be solved to arrive at the solutions given certain conditions. So, we will learn these conditions are either called as the initial value problems or they are called as the boundary value problems. And so, we are interested in talking about numerical approach or numerical solutions to let us start with ordinary differential equations, and then depending on the time that will be available to us at that time, we will decide on the partial differential equations. And these ordinary differential equations are called as ODE, and we will learn how to numerically solve these equations. So, we come across a number of them. The most familiar of them, let us list familiar ODEs are, of course, we are very familiar from our school days as this as the Newton's law of motion. Okay, so, this mass into acceleration is nothing but the force, and there is a differential equation that need to be solved in order to arrive at v as a function of t, and you may actually want to integrate it once more to get x as a function of time, which means the displacement of the body or the particle as a function of time. Then we have seen in electrical circuits, we have seen this differential equation which is called as the LR circuit equation. Okay, which is this L is the inductance and d I dt is the change of current with respect to time. Ri is of course, the voltage drop across the resistance R, and this is equal to the voltage applied. So, this is the LR circuit equation, we are familiar with that as well. Then there are these m d2x dt2 plus alpha dx dt plus a Vx is equal to f of t, and this corresponds to the forced damped oscillator. Known to us, without this alpha dx dt, we would have had a undamped oscillator, just a forced oscillator, and if f of t is equal to 0 and these the damping term equal to 0 is the common equation for an oscillator, simple harmonic oscillator. But with f of t as a forcing term and these alpha dx dt, which is the dissipative term or which arises because of the resistance or the viscosity of the fluid through which the body is moving, we get an equation of this form, and this equation has to be solved, and in order to find x as a function of t. So, that will tell us that how in a viscous medium or a dissipative medium how a body travels, and what are the specific interesting situations that can arise, which are some in the form of resonance and things like that. Then of course, we are only listing a small subset of this. We have a large number of equations that we come across. So, this is the Newton's law of cooling. So, this is the temperature as a function of time, which is equal to some this is the Newton's law of cooling, this is the law according to a body cools. Capital T is the temperature and small t is the time. So, there is the change in rate of change of temperature is proportional to the temperature, and with a constant which is given by K, which of course depends upon the material. Another very interesting one is the law of radioactivity, which can happen in other situation as well. Of course, in biosciences, you can talk about the colony of bacteria or the colony of virus that are decaying according to this law. So, this is the radioactive decay, and one knows that these radioactive decays, these equations are very important in determining the age of a very old sample of rock, and one knows that what is the, if one knows what is the number of atoms at t equal to 0, then one can actually predict the number of atoms at t equal to even after 1000 years. So, by looking at a piece of wood or a piece of rock, one can actually say that what is the age of that, and so on. Then of course, del square u del x square plus a del square u del y square. So, this is a two-dimensional heat flow equation. So, it is a heat flow in 2D. Okay. And there are number of equations which I do not want to repeat here. Schrodinger equation that you know, then there are Fick's law of diffusion and various things. Okay. So, these all these examples that you see here, they denote rate of change of a variable as a function of another variable and other parameters. Okay. So, I think this summarizes that. So, here V is a function of t, and there are these other quantities such as f etcetera are functions of other parameters, like here in the second equation V can be a sinusoidal function or V can be a constant function which is independent of time, and here we are looking at the derivative of current with respect to time. So, how the current is changing and so on. So, these are the differential equations that we come across on a regular basis in various branches of science and engineering, and we resort to numerical methods because most of the time the analytic methods are not available for each of these equations. For example, that we come across the harmonic oscillator, the quantum harmonic oscillator. If you try to solve Schrodinger equation for oscillator potential which goes as half k x square, you would find a solution which is an exact solution, analytic solution, but not without a lot of difficulty. That is, you have to cast that in the form that is available in the form of a special function, and then one can get the results. Finally, we get the result as a function of or rather in terms of a Hermite polynomial which has certain properties, and these are multiplied by a Gaussian function, and this is how one comes across the variety of solutions, but most of the time for any arbitrary potential Schrodinger equation would not be solvable. Like for example, some of these examples that I have given in the earlier slide, they would not be solvable in presence of a very difficult driving parameter. See, the forcing term or the potential, if they are functions of some complicated functions of time, then you may not arrive at an analytic solution. So, numeric solutions are must. Having said that, let us give a few definitions, and we will try to sort of see that what these differential equations they actually represent. So, let us just first distinguish between ordinary and partial differential equations. Because you hear these names the partial differential equations or PDE and so on, you need to know what they represent. So, let us call it as a ODE and a PDE. Here of course, the number of independent variables is 1. So, that is called as a ODE, and when the number of independent variables is more than 1, then this is of course called as a PDE. Okay. So, let us see that if you go to this last page, all these 1 to 5 they represent ODE, because the this dependent variable V depends upon only one independent variable, that is t. Similarly, here the I depends only on t, x depends only on t, the temperature T depends only on time, and n the number of atoms or elements which remain after a time t, that also depends upon time. Whereas, if you see 6, then you see that these u is actually a function of x and y, and that is why you have to take a partial derivative, partial double derivative and arrive at this heat flow equations. So, this is so, in the earlier slide 1 to 5 denote, so if you want the serial number 1 to 5 denote ODE, and serial number 6 denote a PDE. So, this is the difference between ODE and PDE. Let me make this thing smaller. And let us now discuss the order of equations. Okay. So, the order of a differential equation is decided by the highest degree or the highest order, rather, not degree, highest order of the derivative present in the equation. So, for example, if it only involves a first order derivative, it is called as the first order differential equation, we will call it as DE. So, we have say our dy dx is nothing but f of x y and so on, and whereas, so this is first order, because the highest derivative is just a first order derivative, and the d2y dx2 is equal to again say f x y or some other parameter. So, this is actually a second order d. Okay. So, these are this determine the order of the equation. So, we can say that we have a first order differential equation or we have a second order differential equation depending upon the highest order of derivative that is present in the equation. So, let us see these things. So, the first one is actually a first order differential equation. The second one is also a first order differential equation. The third one is the second order differential equation, because the highest derivative is 2, order of derivative is 2. Then it is again the first order differential equation, the last one is second order PDE, the partial differential equation. So, these are definitions of the order of equations. Let us look at the linear and nonlinear equations. Okay. So, what is meant by a linear differential equation and nonlinear differential equation? So, these are of course differential equations. So, a differential equation as a linear equation when it does not contain terms involving the products of the dependent variable or its derivative. Okay. If it does, then we call it a nonlinear equation. Okay. So, say for example, y double prime plus 3 y prime plus 2 y equal to say f of x. Okay. This is the example of a linear DE, because there is no product term, whereas y. So, this f x could be x square or x cube, that does not change it. Say for example, f x is equal to x square. So, that does not change it from linear to nonlinear, because we are only talking about the dependent variable. The dependent variable is y here, y depends on x. So, the independent variable is x and the dependent variable is y. So, that is why this is a linear equation, whereas if you have a term such as y prime square equal to say 1, so this is the example of a nonlinear equation. It could be y prime y, or it could be y double prime y and things like that. But nevertheless, I mean, whenever you have a product term of the dependent variable, then we call it a nonlinear differential equation. And most of the time these linear differential equations, one is able to arrive at an analytic solution, whereas for the nonlinear differential equations, most of the time such analytic solutions are not available. In fact, we will give an example in some time. Let us then talk about the general and particular solution. Consider the differential equation y prime equal to 6 x plus 1. Okay. The solution is simple because you have a dy dx is equal to 6 x plus 1. So, a dy would be 6 x plus 1 into dx, and if we integrate, so we will say integrating y equal to, so 6 x dx is nothing but 3 x square, because 6 x square by 2 and 1 dx will simply be equal to x. But then since we are doing an indefinite integral, we will have to add a constant of integration. Now, this solution represents an infinite family of solutions. So, for each value of c, it is a solution. You take c equal to 1 or c equal to half and c equal to 10, c equal to 100, they all denote valid solutions of this, and you can put it back into this because you want to take a dy dx, and that would because this c is not specified here and it is just a number, it does not depend upon x. So, when you take a derivative, first derivative, this vanishes and it always gives me 6 x plus 1, and so this actually gives rise to an infinite family of solutions, and this is called as the general solution. So, in general, for these differential equations that we are talking about, you will get an infinite family of solutions, one for each value of the undetermined constant that we have in the solution. Okay. Once you specify the constant, then the ambiguity goes away and one lands up with a specific or a particular solution. And this is what we say, that we have y equal to 3 x square plus x is a particular solution. Okay. So, this represents a solution for c equal to 0. So, this is a particular solution that is there. We can of course take a 3 x square plus x plus 1 is another particular solution, which is for c equal to 1, and so on. So, this constant will have to be evaluated in order to arrive at a particular solution, because for a given differential equations you want a particular solutions, and most of the time you do not actually worry about a family of solutions. The family of solutions can exist, but that does not specify the problem completely. In order to specify the problem completely, we need a particular solutions, and to arrive at a particular solutions we need to know this c, and this c can be known if you apply certain conditions which may be known as initial conditions. Okay. So, let us just give an example of that, and these are called as the initial value problems when the initial conditions are specified. Okay. So, consider one equation such as y prime equal to y. Okay. So, this is a particular differential equation that you have to solve, and the solution is simple. You have a dy dx equal to y, and this gives dy by y equal to dx, and if you integrate it, then it becomes equal to log of y equal to x plus c, and then you can actually get this y equal to, we can write this c as nothing but this is, the choice is up to you, you can write it as log a. So, that this becomes, you know, log of y by a equal to x, because if the log comes on the other side, it will become minus, and then you can write it as a you know, the one divided by the other. So, this will give me a y equal to a e to the power sorry, a e to the power x. So, a e to the power x is a general solution, and it has to be determined in order to appear, or rather arrive at the particular solution. So, let us specify y equal to 1 for x equal to 0. Okay. If you do that, then so this is the initial condition. And with this initial condition, we can put x equal to 0. So, y equal to 1. So, this is equal to a. So, a becomes equal to 1, and this allows us to write y equal to e to the power x is actually a particular solution. So, what we were talking about in the earlier slide of the general solution and the particular solution. So, this is the general solution. So, we can reduce the general solution to a particular solution by using the initial condition. Here the initial condition is arbitrarily specified, that at x equal to 0, say y equal to 1, you can take other values of y, that will change the value of the constant a, but you will nevertheless get a particular solution for this given problem. And it is very important to understand that a lot of these physical problems that we come across in science and engineering, they need to be initially solved by hand, and then we would arrive at the solutions by numerical methods. So, some of these solutions need some analytic skills for us to be able to write it in the form that the computer understands, and the computer would be able to decode it and give you a result depending on the initial conditions or the boundary conditions. So, let us look at least one or two this initial value problems. And these are analytic solutions. The reasons that we are spending some time on the analytic solutions, even though you will put it in the computer and want to learn what are the numeric methods in order to solve these equations. But if you have a physical problem, that physical problem has to be cast in the form of a differential equation, which the computer understands and would solve it by the prescribed methods or given guidelines of solving or iteratively solving such equations. So, that requires some analytic skills, and we are going to give two examples for that here. So, a ball of mass m is dropped from rest at a height h. The drag force from the air, so this h, air assumes a form F drag equal to minus alpha m v. It is important to note that most of the time the drag force or the dissipative force or the viscous force are written as proportional to velocity. It does not have to be, but in the first approximation we take them to be proportional to velocity. If the drag force becomes too large, then of course, the several other powers of V could appear, and in real problems in rocket motion and all that, the drag force could be larger than simply linear of V, but here we are going to consider to be linear. So, the question is that find the velocity and height as a function of time. So, the solution is simple, we know about it. So, this is the thing that we have to write. So, this is equal to m dv dt, this is equal to m g minus m alpha v. So, this is equal to, so if you write down this is a dv dt equal to g minus alpha v. Now, importantly note that it is a linear equation, because there is no term which involves v and v square and v prime and things like that. And it's so it's a linear equation. So, it's a linear differential equation, and the degree is of course 1. So, it's given that it's dropped from rest, which means at t equal to 0, v equal to 0. It's at rest at t equal to 0. So, it's initially, when it's initially dropped, it will be that. So, we have to solve for 0 to v as a function of t, and now as we have said earlier, we will use a dummy variable here and a g minus alpha v prime equal to 0 to t dt prime, and if you integrate it, it becomes equal to a v of t equal to g over alpha 1 minus exponential minus alpha t. Okay. So, this is the solution of this equation, and you see that I get a v as a function of t, and every quantity is known. G is the acceleration due to gravity, alpha is the coefficient of that friction or the dissipative force or the viscous force that is there, and this is exponential minus alpha t. So, this is the velocity expression at any given time t. So, it clearly says that as t increases the velocity, this component actually becomes smaller and smaller, and at t large t, this would the second term inside the bracket would go to 0, which would render a constant value, which is g over alpha to the velocity, and this is known as the terminal velocity. So, as t tending to infinity, so v at t equal to infinity, this is equal to g over alpha, and this is nothing but the terminal velocity which a body attains. We are still left with the task of finding height as a function of time, or the distance as a function of time. So, let us see, we can do it here. So, once when we get v of t, so we can write it as dx dt, and this is equal to g over alpha 1 minus exponential minus alpha t. So, this goes from, if you integrate dx prime. So, this goes from x equal to t equal to 0 at x equal to x at t equal to x or h, it does not matter. I mean, we have written it in terms of x. So, understanding that x is the vertical distance that the body travels under these gravitational field and the drag force of the air. So, this is equal to a g over alpha, which is a constant, 1 minus exponential of alpha t prime and a dt prime, and then we are integrating over from some 0 to some t. So, this t is of course a variable t, and then we can integrate this equation. This becomes x t minus x 0. So, this is equal to a g over alpha, and 1 will give me a t, and this will give me a exponential alpha t divided by minus alpha. So, this and then t equal to 0, and sorry, this is not infinity, but this is equal to t. And so, this becomes equal to x of t. Now, x at 0, you can write it as h if you want, because it is dropped from a height h. So, write it as h minus g t over alpha square, g t over alpha. So, this plus and minus g over alpha square 1 minus exponential minus alpha t. Once again, you see that all these quantities are known to you. So, we have arrived at a particular solution of the differential equation, the second order differential equation that we have started with. Of course, we have started with a second order differential equation in terms of x, but we have converted it into the first order by writing it in terms of v. So, this is the solution for this. Very interestingly, you can see that there is a competition as t increases. As t increases, the height tends to increase because of this term, and as t tends to be large. So, this term, the last term, the exponential minus alpha t will go to 0 as t becomes large. So, this negative term will appear. So, there is a positive term as t goes to infinity, and there is a negative term as t goes to infinity. So, they would compete against each other, and any result that you get will have to be physically analyzed in order to arrive at a conclusion. Let us see, do another one which you might have seen in your electrodynamics course. And so, a particle of mass m and charge q moves in a magnetic field the magnetic field is only in the z direction. So, we will write it as 0 0 b. There is one notation that you should get familiar with, because many of these books, especially the book by Griffiths on electrodynamics that uses such notation, these are written in terms of components x, y and z. So, there is no x component or y component, that is a z component is constant. So, there is a magnetic static magnetic field, a constant magnetic field, and where of course, we can write B is constant. The initial conditions are at t equal to 0, that is time equal to 0, are 1, the v 0, that is the velocity at t equal to 0, call it u, which has components in the x and z direction with magnitude u 1 and u 3. Okay. And it has been released from the position r 0, which is equal to 0 u 1 over omega and 0, where omega equal to QB over m, which is called as the cyclotron frequency. Solve dE, solve the relevant dE, and find the trajectory further show that the speed is constant, speed of the particle, of this charged particle. Okay. So, this is clear. So, there is a charge q mass m moving into a constant magnetic field with some velocity. The magnetic field is only in the z direction. At t equal to 0, when the particle was released, there was a velocity in the x and in the z direction, and it has been released from y point, that is where x and z coordinates are 0, but the y coordinate has a value u 1 over omega, where omega is called as the Lorentz the frequency, the cyclotron frequency, which is QB over m, q being the charge and m being the mass of the particle. So, you have to find the trajectory. Okay. So, it is very clear that we have to solve the equation, or rather this differential equation, which is relevant for this problem, which is the Lorentz force equation. So, the Lorentz force equation, so let us write down the solution. This analysis will have to be done before we give it to the computer. The computer will take a certain algorithm and will keep iterating that algorithm to solve at a or arrive at a given result, but this has to be done prior to that. So, it is a q v cross b. So, this gives m dv dt, it is q dr dt, which is v, this is cross b. Okay. So, this has to be done very clearly. R 0 is given as 0 u 1 omega, 0 v 0 is u 1 0 u 3, b equal to 0 0 b. Okay. So, these are the conditions that are given, and v 0 equal to so, this is this is, so v 0 is equal to u. Okay. The components are like that. So, this u equal to this, that is given. So, I start integrating this expression. So, it is a v 0 and v as a function of t, and then there is a dv. So, this is a q r 0 to r at t dr cross with b. So, what one gets is that one solves for this and one lands up with this r minus r 0 cross b plus a u. So, this is the solution of this equation. Now, if you have to really know the trajectory, this one vector equation is not really very helpful. What you have to do is that the trajectory means you have to solve for x, but if you simply solve for r, that will not so very easily give you the feel of the trajectory that the particle is executing in this constant magnetic field. So, what one has to do is that split this equation into components, that is x, y and z components, and we can do that easily because you have b in certain direction, r minus r 0 in certain directions and so on. We cross it and then add the u etc., and then write it in terms of Vx, Vy, Vz, which are Vx is equal to dx dt, Vy equal to dy dt, and Vz equal to dz dt. And then we can write down this, writing it component wise. So, this is a dx dt, this is equal to qb over m y plus u1, this is equal to omega y, because qb over m is equal to omega u1, given that omega equal to qb over m, dy dt, this you have to do it carefully, minus qb over m x equal to minus omega x. So, let us call this as equation A, this is equation B, and the dz dt is nothing but u3, which is equal to, which gives us z equal to u3t. So, this C is particularly interesting. It says that whatever may be your z direction, z is usually the vertical direction, the particle actually displaces uniformly over that linear in function as a function of time. So, as time increases, it goes farther away from the origin in a linear fashion. So, this in the z direction. So, so from A, I can do a double derivative and can write it as d2x dt2 equal to omega dy dt. Since u1 is constant, one does not have to do anything. Now, from B, this thing can be replaced by minus omega x from B. So, this gives that d2x dt2 it's equal to minus omega square x, and needless to say that all of you recognize that this is the equation of a simple harmonic motion, where the double derivative of the displacement is proportional to the displacement, but with a negative sign here, and the solution is very well known. X of t is a sinusoidal function and a cosine function, a cos omega t plus a, let us write it a1 and a2 sin omega t. Now, it is important to note that we have two unknown constants which make the solution as general, but we need particular solutions because we have been given those initial conditions. So, the initial condition is that at t equal to 0, x is equal to 0, because it is from the origin, and then x dot is also equal to 0 if x equal to 0. Now, x equal to 0, if you put t equal to 0, a1 will not allow you to become 0, because for t equal to 0 cos becomes equal to 1. So, you have a 0 on the left, but the first term with a cosine omega t that prohibits it making the this, or rather matching both sides of the equation, and hence this tells that a1 has to be equal to 0. Now, this is an important thing, it comes over and over again, that you have to use the physical condition that the cosine does not become 0, however, the sine becomes 0. If the cosine does not become 0, I cannot have 0 equal to 1 plus 0. Okay. That is a sort of bad equation and should be avoided, we should not even write that. So, we will have to write the a1 is equal to 0. So, only a2 constant remains, and if x dot is equal to 0, we can get x dot t as a2 omega cos omega t. Now, at t equal to 0, the velocity is also 0 in the x direction. So, which tells that my A2 for t equal to 0. So, this is equal to 0, which says that A2 has to be u1 over omega, right, because so this gives A2 equal to u1 over omega, because this is what it comes from this. So, this is so your A2 omega should be at so this so if I do it, I will have to do for the both. So, it is a A1 omega sine omega t with a minus sign, and now you put t equal to 0, you will get A2 equal to u1 over omega. So, if I collate both these things, I get a x of t which is equal to a u1 over omega sine omega t. So, this is the particular solution where everything is known. From B, from the second equation, we also get y dot equal to minus omega x. So, this is equal to minus u1 sine omega t, and so y becomes equal to u1 over omega cosine omega t. So, that is the that is the equation, because we integrate this equation in order to get this. So, this is the second. So, in the in the x direction, it has a sine omega t with some amplitude, and also in the y direction there is the same amplitude and cosine omega t. So, you understand that if x and y, they have the same amplitude, one goes as sine, the other goes as cosine, it is going to be a circular motion, okay, in the xy plane. So, we can write down all these things, because we have already gotten a solution. This one was the for the z. So, we can write down this solution once again. So, x equal to u1 over omega sine omega t, y equal to u1 over omega cosine omega t, z equal to u3 over u3 into t. So, if I take x square plus y square equal to u1 by omega whole square. So, the trajectory is a helix of radius u1 over omega with the axis like OZ. Let us draw this then. I mean, just for my convenience, I am drawing this as the z direction, and this is your O, and this is x, and this is y. So, it is like it is like this. And so on. Okay. So, it just goes uniformly in the z direction as a function, as the time increases, and this thing is of course u1 over omega. So, how far it goes from the this axis, the z axis, it is equal to u1 by omega. We are still left with one question. It's a basically physics problem. Because it involves differential equation, we have brought it up and showed an analytic solution. So, the V that one gets is u1 cosine omega t minus u1 sine omega t. See, we have all calculated the ux, that is dx dt and dy dt, and this is like a u3. So, this V becomes a constant because of this this sine square. So, this is like, so this is like a V x square plus V y square plus V z square, and V x square plus V y square gives a simple u1 square plus a u3 square, and this is nothing but a constant. Okay. So, the magnitude of the velocity of the particle is constant. This is something that we did purposefully, knowing fully well that this really is an analytic method. We are going to go to numeric methods, but these analytic solutions are very helpful in understanding the intricacies or the physicalities of a given problem. So, let us just spend maybe 5 minutes or maybe even less than that in trying to understand that what happened or how people used to solve both the engineers, applied mathematicians and other scientists. They used to solve these differential equations when we do not have computers. So, it is a non-computer method, non-computer method of solving differential equation. And this is they used to do linearization. So, once again let me put this thing in perspective, that we said that it is really required for us to go through certain computer these numerical methods in order to arrive at the solution for most of the problems which are complex enough, so that we do not have an analytic solution. But we are talking about the pre-computer era, when computers were not so easily available, or maybe computation was a big task, and then these mathematicians and these engineers, they followed some procedure called as a linearization procedure. So, which means that even if you have a nonlinear equation, you try to linearize it, that is, you cast it in this form with a n x y to the power n plus a n minus 1 x y to the power n minus 1 and so on, and then a 1 x y prime plus a 0 x y and equal to some f of x. Okay. So, this equation had to be solved, where y n denote not y to the power n, but it denote nth derivative of y with respect to x. And these ai's, that is a n minus 1, a 1 etcetera, these ai's and f, these are specified functions of the independent variable x. All right. So, we could follow this for certain problems, and one example that we all know is a simple pendulum. So, the simple pendulum is just a rigid support, and there is a a length of string and a mass of the bob, and this theta is the angular displacement from the mean position. And there are just two equations which have to be written. There is a vertical force which is mg, and there is a force which will tend to take it towards this due to the tension of the string and so on. So, this is the tension, and if you resolve these two forces, one gets a T equal to something like mg sin theta, and this other one will be rather cos theta and things like that. And then one gets this equation as d2 theta dt2. This is a plus g by L sin theta. This is there in any book on which discusses simple pendulum. This is equal to 0, and this equation, as you see, is a nonlinear equation because it involves sin theta, and sin theta involves all powers of theta, that is theta, theta cube, theta to the power 5 and so on. So, it is a heavily nonlinear equation, but if you observe that sin theta can be written as theta for small theta. both sin theta and tan theta can be written as theta for small theta, because tan theta is sin theta over cos theta, but cos theta becomes equal to 1 for theta small. So, we retain the first term of this expansion of sine, and understanding that the theta cube would be much smaller if theta itself is small, typically like less than 4 degrees. If that is the equation, or rather that is the simplification that we are allowed to have it, then we write it as theta. Now, of course, it becomes a linear equation. So, this is a linearization, linear DE, and this is a linearization that has been imposed as an approximation, and this is a good approximation, because if you take the pendulum too far away from the mean position, it may no longer remain harmonic, and you will not arrive at a solution that you are very familiar with. And the reasons are very easy to see, that the theta cube and theta to the power 5 terms will come, which will inhibit for the equation to give rise to a harmonic solution, and so that the pendulum will not smoothly oscillate back and forth, and the time period can be determined. Okay. So, these are mostly, we have discussed analytic methods of solution of these differential equations. Now, we shall discuss the numeric methods, and there are a number of them, the mostly iterative methods, and we will learn them one by one.